Today I'll be talking about OIM Matrix and forward modeling. Before I start, I want to thank the people I've listed as co-authors here. Eddie Peng, he was formerly a student in Chris Hsu's group at MIT, and he developed some of the pattern center fit information that I'll show. And then Doctors Roach and Griggs are provided the material sample that I'll show today. And also Stu Wright and Matt Now here at EDX. So just some quick motivation for why we should care about forward model indexing if you're already comfortable using Hough indexing is basically robustness to noise and higher fidelity. So here I'm showing an example of a shot peen aluminum data set. On the left is the result when you index it with the Hough indexing, and on the right is the result with dictionary indexing, and you can see that you get a much better result because of this increased noise tolerance, the downside being that it's can be much slower. Here's another example showing some actual patterns. So this is a series collected by Stu of the same sample repeatedly with increasing camera gain, and you can see that as you do a higher gain, lower exposure scan, your pattern quality is going to continuously decrease, and that starts showing up in the Hough, but the dictionary indexing remains quite good until you get to these very extreme noise levels. So what is a physics-based forward model, which is what dictionary indexing uses underneath? Most analysis techniques in science are an inverse problem. For example, in EBSD, we have a pattern and we want to go backwards to an orientation. The forward direction is the physical experiment from an electron beam to a diffraction event to a camera capturing it. And so basically the idea with a forward model is because inverse problems are often mathematically ill-posed, instead you can develop a simulation to basically parallel to the experiment that simulates all of physics that you are relevant. And then you can compare the result of that simulation with your experimental result to determine what your sample was. Here's a little toy example for a problem with more simple physics than EBSD, which is just taking a picture, a normal light picture. So your source could be the sun, you know the spectrum of the sun, or maybe you have a flash that you know what the spectrum of that light source is. You can describe the geometry of where your illumination is, and you maybe know something about the reflectivity and color of your sample, which gives you information about a modified beam, and then you would have a model for the detector itself, so something like a pinhole camera model. And normally the goal with this type of thing is you start with the simplest approximation that you can, and if that is not giving you enough fidelity in your simulation, then you're going to add in more detail until you are appropriately capturing the physics to match what you see experimentally. So this might, in this toy example, mean multiple light sources. You could model the noise level of the camera, or more complicated material models than just a simple, in this example, color. So in EBSD, it parallels this exactly. The EBSD forward model is actually split into two pieces, one for the backscatter yield and one for the diffraction. And then those are combined with this pattern simulation column. So in the backscatter simulation is a Monte Carlo simulation. So your source is a monochromatic X-ray or a monochromatic electron beam. And then it just uses stochastic scattering to give you backscatter yield, and you get it with basically a perfect hemisphere detector. So in a gridded set of orientations, exit directions from your sample, what is the backscatter yield? So that's the Monte Carlo part. And then the dynamical part is basically a block wave approach to say for each energy in a list of discrete energies, what is the full Kikuchi sphere diffraction pattern look like? And then to actually create a pattern, what we do is take these two parts and combine them. So you combine them with the geometry of your detector, and basically for each pixel you say which exit vector from the hemisphere hits this pixel, what does the backscatter yield look like there, and then apply the orientation of your crystal to the Kikuchi spheres for each of those energies and add them all up. And that's what gives you the simulated pattern. And so just to show a little bit more detail for those, here is the hemisphere detector for the Monte Carlo result. So this was a 12 kV incident beam, and I've binned the electrons into 0.4 kV bins, and this is the hemisphere of exit intensity with a stereographic projection at each energy bin. So you can see most of your exiting electrons are at this just below incident energy, and there's this asymmetry because of the 70-degree tilt. And then here is the block wave simulation. If you want, this is the actual expression. If you want more details on either of these simulations, you can refer to this reference down here, which is where they actually develop it. But the result of this conceptually is just a Kikuchi sphere, the full diffracted intensity for every direction. And so you'll do one of those for each of the energies that you have binned in your backscatter yield. And as you can see, as you go to lower energies, you get these wider bands. And then here's the combination. Take the exiting directions plus the master pattern, apply your geometry, and that gives you the diffraction pattern for one energy, and you just average them all together. And so that's how we get these realistic patterns. And the question is, now that we can simulate these realistic patterns, how do we use that to index our experimental data? So there's basically two problems. Which of the patterns is the most similar, and what are all the patterns that we care about? And you could do different approaches for those. In practice, what Matrix and the original paper do is use a normalized dot product. That's nice because it is invariant to the things that we care about the most. It is invariant to the image processing parameters that we don't care about. So it captures the things we care about the most. And then for all the patterns that we care about, you just grid all of orientation space. You have to pick some resolution. Normally, it's not practical to use a very fine grid, so we'll use a coarser grid and then do a subsequent refinement step. And you have to do this for each phase. And in practice, you end up needing to do something in the 1.5 to 2.5 degree resolution. If you go beyond that, you start having trouble with indexing. And if you go much below a degree or a half a degree, then the size of the number of patterns you have to simulate really blows up. So this is just showing, as a function of the angular resolution and the point group due to the symmetry, how many different patterns are there to index. So you can see that for low point group symmetries, this can become extremely expensive. And here's just visually showing you that you need sort of that 2 to 3 degree resolution before your closest simulated pattern is too far away from the experimental pattern to give you a good result. And that's reflected both in the noise and in what the maximum dot product is. And then, like I said before, you have to do this refinement step because you're just finding the closest grid point. So you then have to do basically a nonlinear optimization for each point to get rid of these steps or mosaicing, if you can see here, to get a nice smooth result that's equivalent to the Hough indexing result. And the way that this works is you have to optimize normally not only for your 3 degrees of orientation freedom, but also for the pattern center, because for larger scans, you expect to have a shift in pattern center over the sample. And this can be pretty slow. The existing code can simulate about 2,000 patterns per second. And so it's really not possible to do brute force gridding. You need to do something slightly more intelligent. And you basically have this trade-off where the bigger your dictionary is, the smaller the steps, the less you have to do in refining, but the longer the dictionary takes. So there's this trade-off where we want to sort of optimize the time, the overall time, as a trade-off between a really large dictionary being slow but making the refinement faster, and vice versa. So the existing code in Matrix, which is what is also in the EMSoft implementation, is this BOBYQA, bounded optimization by quadratic approximation. And basically the idea is you have your 4 grid points. So in these schematics, the black circles are places where you have simulated a pattern and evaluated the dot product. The green is sort of the true continuous dot product function. So here, this very dark green, that would be our peak, the true orientation. That's going to give you the best dot product. And as you get further from that orientation, you'll get a lower dot product. And the gray is sort of a proposed next place to evaluate. So what BOBYQA does is you start with your 4, or in 3D, because of the 3 degrees of orientation freedom, 8, but conceptually the same. You start with your grid points, you fit a quadratic to these and say, based on the value of the function I've measured at these 4 points, where would the peak of the best fit quadratic lie? And that's this gray point. You evaluate that function, you update your quadratic fit, and you keep repeating until you reach some convergence criterion to say, yes, this is the peak. And so basically the problem with doing sizing your dictionary is that you need to make sure both that you are close enough so that your constrained search actually contains the peak, and that your dictionary is small enough that you can actually find the peak. And so this bottom thing is the situation that happens when you're start increasing your dictionary size to be 2 courses. You're basically potentially going to be so far away from the peaks that you can't even see it. And to do a pattern center fit, we want to basically do the same thing, except it becomes this complicated problem of you need a good pattern center to get a good indexing, and you need an indexing to fit your pattern center. So there's basically 2 approaches that are currently used. One is something like I showed before, where you have the you use this more sophisticated nonlinear optimization with an expensive approach like a forward model, and the other, which is the current auto pattern center fit in analysis, is use some cheap metric like a Hough index-based approach, and then just do a brute force grid. And you can see that this brute force grid approach, if you apply it to the dictionary result, does not give you, it becomes intractable very quickly. This would take, if you did a 2 degree grid, covered a 2 degree orientation search at 1 degree resolution, and a 4 pixel window on where your pattern center is at a 1/10 of a pixel, it would take an hour to brute force it, which is not really realistic. And the problem for that is that the simulation is very slow. And so what we have, I believe, coming out shortly in analysis is we've switched over from a CPU-based pattern simulation to a GPU-based pattern simulation. And this gives you a significant speed up. You can compute, instead of about 2,000 patterns per second, something more like 20,000 patterns per second. And that opens up a lot of flexibility because, first of all, if you are familiar with the dictionary indexing in Matrix, you no longer have to pre-compute your dictionary because they are fast enough to compute that you can just build them on the fly as you need them. It makes a brute force approach more tractable for some situations, and it also just gives you more flexibility with other things you can try that are similar to that BOBYQA, but maybe require more evaluations or something like that. And so just to show an example of that, I've implemented a pattern center fit with a particle swarm optimization. And the idea for particle swarm is you basically, it's sort of between BOBYQA and a brute force. So it takes more evaluations, but can cover a wider space. So the idea is you throw a bunch of random points to test on here, give them all a random speed and direction, evaluate the function at each one, and then at each you do like a time steps, and at each time step, each particle moves. It turns towards the best point that has been found so far. And so it should give you more robustness to local minima. Here's a function with ISO curves showing you have all these different local minima, and it finds the true minima pretty well. And here it is applied to pattern center fit. So here on the left is my initial starting guess, just to show you how bad of a fit it can work on. And then on the right is actually also animation flipping back and forth between the fit pattern center and the true value. And here, just because you can't really see it, is the difference in percent and in 8-bit gray levels. So basically everything is within 1 or 2 gray levels. And this recovered about a 20th of a degree in orientation error and a 20th of a pixel in pattern center error. And you can basically just start with sort of a generic value and get a good enough answer. And to do, if you spent the same budget on doing pattern simulations with a brute force grid, you would only be able to grid at about a degree of resolution. And so here I show this applied to some real data that we care about, and this is courtesy of the researchers I mentioned at University of Mississippi. So what I did here is I took 9 grains in this data set. This is showing image quality, and here are the patterns that I've pulled out of those grains, and then I applied NLPAR with a very big window to get really nice starting patterns. And then I applied that particle swarm optimization to each one, and this is the result of the median of the fit pattern centers. So this is all simulated with a single pattern center, flipping back and forth between experimental, which is a slightly brighter, and the simulated, which is slightly darker pattern centers. And then the red, that's the normalized dot product. So you can see that this has done an excellent job of fitting the pattern center. And just to compare with some other methods, so BOBYQA, which I showed before, the Hough-based approach, and this I used manually drawn bands, and this snob fit, which is the approach from Eddie Peng. And so they all, the BOBYQA actually had difficulty with local minima, but the other results all agree quite well. The difference being that for this analysis approach, I had to draw the bands manually to get a very good result, and the snob fit approach can be pretty slow.